Thank you, Jim. Yeah, I saw Kareem's lecture, which was excellent, and I have absolute conviction that E plus E minus is a fantastic environment to do flavor physics for the reasons Jim says. But what I'm supposed to talk about and what I'm supposed to convince you about today is that Hadron Colliders are arguably the ultimate place to do this sort of study. So my first lecture will address the question of why study flavor at Hadron Colliders and how we do it. So here is the plan of the 4 lectures I'll be giving. I'll talk more about today's lecture on the next slide. Next week in my second lecture, I will address unitarity triangle measurements and CP violation. After that, flavor changing neutral currents. This is the sort of stuff which Kareem has been talking about. And I will conclude on Tuesday, if I get that far, with charm physics and also future prospects in this area. As Jim says, I've been involved in LHCb a long time, so I have an LHCb bias, and without question, LHCb is the Hadron Collider flavor experiment, so it's unavoidable. I will talk about it a lot, but there are places where it's apposite to feature other experiments, and I will do that where appropriate. So, okay, today's lecture, let's look at why we should study flavor at Hadron Colliders. And then if you do that, you don't need any experiment, any old experiment, you need a dedicated experiment. And I will explain the reasons for that, accompanied by some historical notes, which I hope will be of interest. Now, the dedicated experiment we have is LHCb, and I will talk through the reasons why LHCb is special in terms of its geometry, the operating choice of luminosity, the instrumentation, and I'll say a lot about the trigger and the data challenge. Towards the end of the lecture, we should be talking about what we can do with this experiment, and I've chosen, rather than to start talking about flavor physics, which is, of course, the topic of the lecture series, I think it's unavoidable and very correct that we say some words about the topic which is not flavor, that is hadron spectroscopy, because flavor experiments are excellent experiments to do hadron spectroscopy. So this will be a digression at the end of today's lecture. Okay, so Kareem showed you the beautiful and exquisite physics you can get out of Belle and Belle II. You see on the left, this is an event display at Belle II, and you see how clean it is. You can see exactly what's going on. Flavor physics studies consist of precise measurements of delicate and rare processes. So this is for sure the place you would like to make these measurements. On the right, you see a high pileup event at CMS, and you see this is just a mess. It's horrible. So surely, if you want to do flavor physics, you'd like to do it in a left-hand environment. Expanding on that, because of the complexity of the event, the backgrounds are much higher at the Hadron case, and this becomes particularly difficult when you have neutrals, because you cannot vertex these. You have the problem of the trigger, which I'll say a lot about later, and then there's other issues unrelated to the event complexity, which makes E plus E minus upsilon 4s experiments very nice. I will talk about flavor tagging in the next lecture. So this is surely a no-brainer, an open and shut case, but not so fast. If you look at the cross-section, the production cross-section, if we compare the epsilon 4s and E plus E minus, that's about a nanobarn, I believe. And if you look at BB bar at LHC at 14 TeV over the full solid angle, that's 600 picobarns. So that there's a absolutely colossal difference in the production cross-section. So the B factories and Super Belle II and Belle II run at a very high luminosity. So this compensates to some degree, but even folding this in, you get a colossal difference in BB bar production rates. This tends us, this sort of favors the Hadron machine. The Hadron machine also, here we are producing all B Hadron species, of particular interest, the B sub S, the lambda B, and the B sub C, which are not available at the epsilon 4s. So this opens a new vista of physics. And those particles which are produced with a high boost, and this is very good for doing time-dependent measurements. So we must take hadron machines seriously. And indeed, historically, the hadron environment has yielded very important results in flavor physics. For example, the B quark itself was discovered there. So this is on the left, the plot of the epsilon discovered by E288 back in '77. So this was a fixed target with a proton beam. UA1 was the first experiment to actually discover BB bar mixing. This was rapidly accompanied by Argus. And the observation and resolution of BS oscillations was performed with this very beautiful measurement by CDF in 2006. So there was a rich tradition of great measurements made in the hadron environment. So we think of the hadron environment, and today, what does this mean? It means this 27-kilometer collider nestling next to Lac Le Mans in Geneva, under the foothills of the Jura. So this has 4 interaction regions, and of course the ones which are of highest prominence are those which house CMS and Atlas, where the Higgs were discovered. So the question is then, Atlas and CMS, these are beautiful experiments, very hugely expensive experiments, and they're very well equipped. So surely they can do flavor physics. And here you see CMS asking that very question. In answering that question, I would say yes, they can. They are exceptionally versatile experiments, and as I will show you, they have produced high quality results in flavor physics. But their studies are restricted to final states involving dimuons. This is a restriction of the trigger, and they have no hadron identification capabilities, no particle identification, something I will speak about. So this puts many, many important measurements out of reach. So Atlas and CMS, superb experiments that they are, that we need something better, or at least something different, something dedicated if we want to really exploit the flavor potential of the LHC. And this was appreciated right back in the 90s when people were deciding what experiments they wanted to place on this machine. There were communities then, they'd already been on the SSC as well, who were thinking about a B physics experiment. So this is a historical note that at that time there were 3 proto collaborations. Gadget, which was a fixed target proposal. They would actually inject the LHC protons onto a gas jet. And this had a calorimeter trigger, which we'll see is an important feature of LHCb, which gives good efficiency for hadron final states. There was an experiment proposed called LHCb, which the idea was to extract the LHC beam halo with a bending crystal, a very cute idea. But then there was one called COBEX, which was pushed by the UCLA group of Peter Schlein. And in contrast to the first 2, this was a collider experiment, and that's very, very important. Though the first 2 proposals would use the LHC, they would use it in fixed target mode. If you're at the collider experiment, you get the full 14 TeV center of mass energy, and this means a much, much higher cross section than you get in fixed target operation. COBEX also proposed to have a vertex detector sitting inside a secondary vacuum, which could be used for triggering. I just want to actually say a couple more words about this, because this is absolutely critical to the success of Hadron Collider dedicated experiments. And indeed, COBEX were able to convince the community that this was the way forward, because there had been a proof of principle experiment operated at the SPS by the same group a few years earlier, called P238. So the idea here, what one has, it's a sequence of silicon planes very, very close to the beam axis. Now this will look very reminiscent, those of you who already know about the LHCb Valo. And these were put in so-called Roman pots. So these are in secondary vacuums in boxes which could move up and down. So the beam would be injected when and the boxes would be retracted, and then they would move closer. And they were able to record these tracks with very, very low background. There was a worry that background would be a big problem, but they've seen these tracks and you see these beautiful vertices, and that convinced people, as stated in this abstract here, unfortunately with the word accommodate misspelt, that such a detector was possible, and this gave a conviction that this was the way forward. So these three experiments were encouraged to group together and essentially around a Cobex ideal, but with other aspects. For instance, the calorimeter trigger of a gadget was proposed to be included, and these people were encouraged to develop a detector concept that merged the best features of each. So this is what we did in 2000 and in 1995, a long time ago now. The letter of intent for LHCb was released. And the idea was to operate in collider mode, benefit from the full cross section of the LHC, and have good trigger efficiency across a wide range of B hadron decays. Let's just pause there and just acknowledge that things were happening elsewhere in the world as well. Some words about HERA-B. So when you look back at high energy physics experiments, some are famous because they were very, very successful. They did great things, made great discoveries. And some are famous because they were absolute nightmares for the people who worked on them. And if you meet a person from these experiments, I won't list them all, we have our own list, you treat them with respect because they've been through a very hard time. And I treat people who worked on HERA-B with respect because they had a miserable time. And that's because they were trying to do something very, very challenging. So HERA-B, the idea was to use the HERA proton beam and then fire that on a fixed wire target. And you see this schematic here, you see a spectrometer which looks rather like LHCb. Sometimes people see LHCb and they think that's a fixed target experiment. It's not, it's a collider experiment, but HERA-B was a collider experiment. So the idea was that they would produce bees in this fixed target, and then they would be able to study B to J psi K short, which is the golden channel for CP violation. They wanted to be the first people in the world to measure sin 2 beta, which is something we'll talk about on Monday. This was an incredibly challenging, very demanding, goal, because they were operating at 920 GeV center of mass. B bars are produced there, but at a very low level compared to the background. The ratio of signal to background is something like 10 to the minus 6. This is to be contrasted with 10 to the minus 2, which is the case at collider mode at the LHC. And they were wanting to operate at very, very high rates, tens of megahertz with pileup. They needed this to get the event rate. So this actually is this is actually much harder than what we've set out to do at the LHC and what we're doing now. And not surprisingly, it didn't work very well. They had lots of problems, particularly learning about aging of their MSGCs. They had problems with material. The triggering was very, very challenging. And in the end, they got overtaken by the B factories. So HERA-B ceased data taking in 2003, and they never reconstructed and made this measurement. But it was still a very valuable experiment because we've learned much from it. So the triggering, operation of the vertex detectors and the riches, which were very successful there, and lessons about what not to do have been very important for LHCb and other experiments. And also, if we look across the Atlantic to Fermilab, that of course had the tevatron, and proposed there was a dedicated experiment called BTEV, which was rather similar to LHCb, but with 2 arms, so 2-arm spectrometer, and some small differences. The idea was to use a pixel, not a strip vertex detector, and there was some higher emphasis on neutral physics. So this was, these people were developing very valuable ideas, but unfortunately, though it was given a first stage approval in 2004, it was later cancelled. LHCb again benefited. We attracted great collaborators from BTEV, for example, Sheldon Stone and his group, and some of the aspects of the BTEV concept are going to be central to our upgrades, which I'll talk about in lecture 4. But anyway, back to the LHC, back to this experiment which coalesced out of Gadget, LHB, and Cobex. So LHCb is a dedicated experiment for flavor physics at the LHC. As I explained, Atlas and CMS, though wonderful, have some limitations. How dedicated? Well, it's dedicated in the sense of its acceptance, its operating luminosity, its instrumentation, and the trigger. And we are going to now walk through these and explain why things are as they are. So firstly, the geometry. So, you know, if you have the money, you instrument full 4 pi or as close as or as much of the solid angle as you can. This is what Atlas and CMS do. They certainly have the money. And also their physics is produced in the central region. Now, by the energies of the LHC, B hadrons are rather light things. So when they are produced, they are thrown forward. They're produced predominantly by gluon-gluon fusion. So if you can't instrument the full 4 pi, the best compromise is to go into the forward region. That's where you'd like to build your detector. And having made that decision, that there are other great benefits which come from that. So for example, you can get your vertex detector really close to the beamline. You get a high boost in that direction. You get lots of space because you have about 20 meters of space in even the existing LEP caverns. And in terms of high PT, and this is high PT in the B physics environment, so we'll be talking in Hadron Colliders a lot about PT. So by this we mean transverse energy with respect to the beamline. You're after a PT which is pretty much that of the B mass. So when the B decays into its particles, they each will have up to 2 or 3 GeV, maybe a bit more, because the B is produced itself with some PT. So by going into this region, you can go down to really quite low high PT if you will excuse the tautology. So that motivates the geometry. If you're going really close to the beamline, you have another problem though, and that's of radiation damage. So Atlas and CMS are operating at 10 to the 33, 10 to the 34 now, centimeters to the -2, seconds to the -1. If you're getting really close to the beam, you can't do that because the radiation damage on your silicon detectors becomes enormous. Furthermore, you get this huge pile-up, and this makes you get many interactions happening at the same time in a given crossing, and that makes the flavor physics very difficult to do because it's very difficult to pick out all of the tracks you're interested in from your B decay. So it's so what makes a lifestyle choice? The lifestyle choice for B physics at Hadron Collider is to go to lower luminosity. You might say, well, how can you do that? A Hadron Collider is a Hadron Collider. It has its own luminosity. Well, it doesn't. So you see very clearly here from this event display taken from a typical fill that Atlas and CMS start with very high luminosity and it falls away exponentially over a period of several hours. At the LHC-b interaction point, the 2 beams are at the start of the fill, they are purposely collide, so they are not head-on. So they are just grazing each other, and that gives you a lower luminosity. And as the beam currents drop, you move the beams closer and closer and closer together, so they get more and more head-on. And in that way, you can maintain a constant so-called leveled luminosity throughout the fill. And this is what LHCb did throughout runs 1 and 2 of the machine, ending up at a luminosity, operating at a luminosity of something like 4 10 to the 32. So that's the geometry and the luminosity explained. Now let's talk about the instrumentation. So we have this good forward spectrometer. It's LHCb, it's about 18 meters long. It has to fit into a caving which was already in existence, which was used on LEP, the previous collider, E plus E minus collider. One sees on the left, this is the interaction point. So the PP bars collide here in this yellow thing, and that is the vertex detector. And then the particles which are produced, they go in all directions, but the ones we study are thrown to the right through the magnet, that's a dipole magnet, tracking stations, another rich, the calorimeter, and the muon system. So let us talk a little more about this. Firstly, and I want to say a few more words, particularly about the vertex detector. Before I do that, excuse me, let me just say something very important. I'm showing you this as if it's an experiment that exists. It is not. This experiment no longer exists. This is the experiment that operated for runs 1 and 2 of the LHC. You may have noted on last Friday that run 3 of the LHC is now officially started, and now sitting in the IP8 where LHCb was. It's still called LHCb, but it's an upgraded detector. It's very different in many aspects, and I will explain this in lecture 4. So anyway, coming back to the experiment which did the physics we will be discussing, let's talk first about the vertex detector, or vertex locator, or VALO, as it is called. So this is a silicon strip detector which sits around the interaction point. Here you see it being produced in the lab, so it has 2 halves. Each half is, you see in the middle here, this is the sensor, this is the region which is sensitive to the particles. So it looks like a sort of half of a compact disc, and around here is the readout electronics. In the middle, there is a hole. We'll see that more clearly on the next slide. Oh yes, let's go to this slide. You see this again very clearly here. You see the hole in the middle, and that's where the beam goes down. So you might be saying, well, I'm just seeing half a detector. What about the other side? Well, one has 2 halves of these, and they come together. I'll flick between some slides here. So on the right here, you see a proton's view as it goes through this down the region right in the middle of the VALO. So you see on the left 1/2 of the VALO, and on the right you see 1/2 of the VALO. And you note that these 2 halves are separated from each other, and in injection, those 2 halves are indeed separated from each other. They're kept several centimeters apart. So the VALO is actually immovable, but then when stable beams are declared, these 2 halves are moved together, and then what the proton sees is, you see it here. So this is actually rotated. This picture is rotated with respect to the previous view, but one sees this the 2 regions of the VALO coming flush against each other, and one sees this region in red here is where the beam goes, and to give you sense of scale, there's a €1 coin around it. Okay, so this is the VALO. I mentioned radiation damage being a concern. It was a concern, but the VALO, which was built for runs 1 and 2, performed well and survived right until the end. Here we see a picture at the bottom, which is a measurement of the efficiency of this VALO, essentially almost at the end of run 2, and it's red, and red is good. This means high efficiency. So one sees that despite the radiation it received, this intense blast it received for the years of operation, it maintained a high operational efficiency. Let's move on from the VALO and talk about the other detector, which is very, very specific to LHCb and very important for flavor physics, and that is the RICHs, the ring imaging Cherenkov detectors. There are 2 of these, one RICH 1 upstream of the magnet, and one rich 2 downstream of the magnet. And I'll explain why we need 2 in a second. But the rich it consists of a radiator in which the traversing particle, if it's going fast enough, will emit a cone of radiation, Cherenkov radiation. And this cone we'd like to, it's then reflected by mirrors. Here you see some mirrors in the lab here, and it's reflected onto an array of photodetectors. Here we see the photodetectors. And what you want to do is to image this cone, and when imaged, you see it as a ring, and the size of that ring, the opening angle, is related to the velocity of the particle. And since you know the momentum of the particle through the tracking system, you then can determine its mass. And here you see a very nice picture on the bottom of, against momentum, different particle species, the measured angle. So as each particle comes above threshold and emits radiation, one sees it with a ring angle which varies with momentum. We need 2 of these rich systems because we want to cover the full range of momentum at which we want to do physics. So this is a critical difference between the LHC and Hadron machines and the E+ E- environment which Kareem was talking about. When you are at the epsilon 4s, the particles which are produced, you're at BB bar threshold, so their momentum is very limited, and it exists in a rather restricted range. So you need particle identification there, just as you need it at the LHC, but the range of momentum you have to cover is very narrow. And that means you can do it with threshold counters, as Belle did, or the Dirk, as Barbar did, or the top, as Belle II are doing. When you go to the Hadron machine, you need to cover a much bigger range of momentum. You'd like to do physics between 1 and 100 GeV. Oh, the scale here, it says MEV, it's GeV. Oh no, the scale is correct, there's a 10 to the 3. So you want to go from 1 to 100 GeV, and the only technology which can do this is a ring imaging Cherenkov detector. And one alone will not do it because the range you can cover is dictated by the radiator you have, and therefore you need at least 2 radiators to actually cover the full range. And that's why we have 2 riches in LHCb. One covering lower and middle momentum, which has C4F10, and the other at higher momentum, which has a CF4. And here one sees how well this apparatus works. So this is a plot showing the efficiency for identifying kaons as kaons, and this is shown in red. And there's 2 lines because one constructs a likelihood and you make a cut, and that cut can be whatever you want. It can be loose or tight. So let's just focus maybe on the open markers here, which is the loose cut. So one gets efficiencies which are over 90% through the full 100 GeV momentum range. And then you want to compare this with the misidentification rate, the probability of a pion being misidentified as a kaon. This region is very, very low. It obviously rises with momentum and goes up to about 30% right at the top. But one can change the cut and move this down to a negligible level if one wishes. So this is the particle identification provided by the rich system. And to give you a sense why this is important for the physics, we'll see many examples of this next week, but I think we should make a connection to the physics here. One example, for example, is 2-body charmless B decays. So things like B to pi pi, or BS to KK, or B to pi K, or lambda B to PK, etc., etc. These are all channels where B hadron has decayed into 2 charged tracks, and it's done it. The final state does not involve charm, and each of these channels carries very, very interesting physics and very different physics. So you want to analyze them separately. But if you reconstruct the invariant mass of the 2 charged tracks under, say, a pion hypothesis, then all of these will merge together, and you get what you see in this top left plot here. So all of these contributing channels are superimposed, and physics becomes impossible. So that's one example where you absolutely need a rich. And you get this rich and you turn it on and you dial up, you say, I want a kaon and a pion, or a proton and a kaon, or proton and a pion. And then each of these individual signals then pops out at you, and you get rather clean signals of each. So this is a vivid demonstration of why the rich is important and how well the rich works. I like this collection of plots, but this comes from very early LHCb data. And you see the background levels are not enormous, but substantial. Since then, we've learned a lot more. So let me just flash in front of you some analogous plots reconstructing k pi, pi pi, and BS to kk. This is with Run-2 data. And you see that these signals are exquisitely clean. So this rich system has really worked to treat. Okay, so continuing our tour of the spectrometer, but being more brief, because what we are discussing now is more standard. One needs a magnet, of course, and LHCb has a 4 Tesla meter dipole magnet. One needs the tracking detectors. So these were straw tube detectors with silicon right in the middle part. And downstream, one has the calorimeter system and the muon system. So the calorimeter system and the muon system are very important for triggering, which I will describe. But also offline, there's an enormous amount of physics, particularly associated with muons. That is the instrumentation. But now let us turn to a topic which is absolutely central, not just LHCb, but any Hadron Collider experiment. This is a big difference with respect to E plus, E minus. Any Hadron Collider experiment stands or falls on its trigger. So this brings us to the data challenge. The point is that the actual amount of data that's getting thrown at you in these PP collisions is enormous. It's like being exposed to a hose pipe. So one has to be selective. To give you a sense of scale, the LHC operates at 40 megahertz and about 15% of the year. So data is coming every 40 megahertz. And these enormous detectors are recording signals. But if one tries to integrate this over a year, let's consider what this means. So the LHCb experiment, it has a raw event size of about 100 kilobytes. So that's substantial, not as much as Atlas or CMS, but it's still a lot. So that brings you to 15,000 petabytes per year. And this is raw data alone. So that is probably less than is dealt with by search engines, but it's still considerably more than Facebook. I looked up Facebook at the moment is operating at about a factor of 10 less than this. So you might think that we just store this data. It's much less data than Facebook are dealing with. We should be able to manage this. But if this schematic on the right-hand side makes the problem very clear, I mean, the problem is obvious. Facebook may have less data, but they have a lot more money. Their computing budget is, I think, 2 orders of magnitude higher than ours. So we can't just store these data. We have to be selective. We have to do something smarter. Public science has less money. We have to do something better. So we try and process as much of this in real time, and this is motivates the need for the trigger. And we're helped in this by the fact that though we have this huge event rate, that not all collisions are equally interesting. The core business of LHCb is beauty physics, and here we can be selective. So the collision rate is 40 megahertz. It's actually a little bit less than this due to empty bunches, but this sets the ballpark. B hadrons are produced about once every 150 pp collisions, and much of the physics we're doing is focused on specific decay modes, which are not overly common. So to take an extreme example, BS to mu mu occurs once every 4 × 10⁻⁹ BS decays. But there are certainly more common ones that we're interested in, and typically they have branching ratios of 10⁻³ or something. So we can be selective. The problem is a bit more complicated for charm, and I'll talk about this in my final lecture. But we only save to disk the potentially interesting collisions, and this is the task of the trigger. So how do we make a fast decision, because the trigger should be fast, of what is makes the event interesting? So this I'm sure you know, but let me just cycle through it. Let me take the example of a B decaying to 2 muons and a kaon. Now there are characteristics of increasing complexity that can be searched for to determine if the collision is of interest. So we can look for high transverse energy, which I've spoken about before, or momentum of these decay products. These typically for B decay will be of a few GeV. So that's something you can do rather quickly in hardware in your experiment. This is the earliest level of triggering. After that, and this requires software, you can look for tracks which have a significant impact parameter with respect to the primary vertex. Primary vertex is where almost all the tracks come from, but the B travels some distance, about 1 centimeter, so that if you line these tracks up back, they will not coincide with the primary vertex. This is your impact parameter. And then if you have the tracks, all of the tracks, you can try and join them together in a vertex, which again should be displaced from the primary vertex. This is the secondary vertex, or the B hadron decay vertex, and this is the primary vertex. So each successive step provides improved discrimination, but it requires more information and time to execute. And in LHCb, the first step is performed in what we call the L0 trigger. That's a hardware trigger. Next to in the high-level software trigger. So here is a schematic of this on the left. So this white box is the L0 hardware trigger. This is what we've spoken about. Essentially the decision is made within 4 microseconds. Then the data are retained in a pipeline at the front end of each subdetector. And then when we've decided that indeed the event looks interesting from the L0 point of view, then the event will be retained and the whole of the detector will be read out. And that reading out happens at an event rate of about 1 megahertz. So that's a lot. And it's a lot more than, for instance, Atlas or CMS do. Atlas is at 75 kilohertz, I think. And that's because B physics, there's a lot more B physics going on than Higgs physics. Then one has the high-level trigger. So now you've read the event out, and the event is then put into CPUs on what we call the event filter farm. So this was a set of PCs, something like 1,700 nodes located at the experiment. So the event was assembled and put together, and there are 2 steps were performed. The first one where you look for these tracks with impact parameters, that's HLT1, and then after that HLT2, where you try to fully reconstruct the event using all the event information. And then when you're convinced the event is of interest, you write it out, and it was written out at a rate of something like 12.5 kilohertz. Now this HLT1 and HLT2, I mean, traditionally, well, many experiments have operated like this. Essentially, Atlas and CMS operate like this. And what you might imagine is that you just perform these two steps, one immediately after the other. And this is indeed how LHCb started. But through time, we evolved to a much smarter, much more efficient, very cunning scheme. What we did is after HLT1, so this is the events here are being processed in HLT1, essentially immediately that they have been recorded. But we then wrote them out onto a massive disk buffer, 10 petabytes. And this buffer is so large that one could actually just continue to write events out there and keep them there for a period of 2 weeks if necessary. And why did we do this? That was because we were then, we started to look at these data, we started to align and calibrate this data. There's many parts of the experiment which fluctuate with time. For instance, the velo is moving at the start of fills. And then when we were convinced that we had excellent control of the alignment and calibration, we processed the data on this disk and then applied a full offline-like quality reconstruction so that the high-level trigger 2 decision was the absolutely best decision you could make, and one which was, you know, of offline-like quality. So that meant that the last stage of the trigger, rather bizarrely, could actually be run even 2 weeks after the data were collected. And only then was it written out for offline storage. So this has the two benefits that the trigger is using offline quality information to make the decision, and also that there's no need for a further offline processing step afterwards. Now, offline processing is a big headache for high energy physics experiments, but we just wrote this to storage, and that's your event done. And indeed, some of these events, those categories of events which were appearing at very high rates, in particular charm physics, these we would actually write out not the everything which was reconstructed, only the things which are relevant for actually reconstructing the decay of interest. So these were a highly reduced format, and this was reserved for certain physics lines, and this made things particularly efficient and very suitable for rapid analysis. So this scheme, this is a paradigm shift in physics experiments. So that's why I've spent some time speaking about it. We call it real-time analysis, and this is something which is now becoming more and more widespread. So things of this sort are being adopted for the high luminosity LHC and for future experiments. And a final remark is that the rate at which events are being written to take, that's 12.5 kilohertz. That's a lot. If you compare to Atlas, Atlas writes out events at something like 600 hertz. The Atlas events are much larger, but the fact that LHCb writes out at this very high rate is a reflection on the wide scope and large sample sizes of flavor physics. Okay, and this is a plot showing what how the trigger performs, the efficiency of the trigger. The plot is a little more complicated than I'd like it to be. What you see on the bottom are different event categories, and let us just focus on blue, I think, for the discussion. That shows you the efficiency the overall trigger had. So with this trigger scheme, one cannot get to 100% efficiency, but you get very close to it in channels like BS to mu, where you have two muons, which is easy to trigger on. But in these other channels, you see that though the efficiency, it can drop to 30% for this is D star to D0 K pi pi. So this is these events have relatively low PT in their hadronic. They have relatively low efficiency, but 30% is still plenty enough to be doing physics with. And one has a good trigger efficiency across the full range of B decays, both those involving leptons, those involving hadrons also, and this is critical. One can perform a full physics program. Okay, LHCb has collected so far something like 9 inverse femtobarns, and that will be, and this corresponds to something like 10 to the 12 BB bar pairs produced within the spectrometer over the full run 1 and run 2 of the LHC. So this is the enormous sample, and we will be seeing what physics can be done with that sample. And indeed, in the final 5 or 10 minutes of this lecture, I want to take my first physics topic, and I've purposely chosen actually not to plunge straight into the pure flavor physics, but to talk about something else. That is hadron spectroscopy. So this is not to do with weak decays. This is non-perturbative QCD. But the most interesting studies one can do in this regime are involving states with heavy quark content, and this is ideally suited to flavor experiments. This is something which was not actually foreseen when LHC was and the experiments were being conceived and designed, but it's been LHC has been truly a goldmine for spectroscopy studies. You may ask people what particles have been discovered at the LHC, and people will say the Higgs, and then they will stop. The Higgs is just the most spectacular example, and certainly one which we cannot downplay its importance. But in fact, not one new particle has been discovered at the LHC, but 63, the Higgs, and then 62 new hadrons. And here you see them plotted against time. And here you see the now plotted against math. So we could, you can go to talks and go to conferences when each of these is explained in loving detail. We don't have time to do this, and we would lose sight of the wood for the trees. So I'm just going to say a few words about exotic baryons, essentially pentaquarks. And this is something which is, I think, important. It's unique to the LHC because these baryons cannot be produced at the upsilon 4s. So just to introduce this, all those states you looked at, they can be classified in two ways. They can be classified as fitting into the so-called vanilla quark model. Going back to the birth of the quark model, Murray-Gell-Mann, you know, the quarks were designed so three quarks would make up the baryons we know and love, and a quark-antiquark would make up the mesons. So there have been plenty of discoveries of such particles. Here are two examples on the left, both made at the LHC, one by CMS, one by LHCb. But one also has the possibility of exotics. So one could make a baryon out of 4 quarks and an antiquark, and a meson out of quark, antiquark, quark, antiquark. And people look for these for a very long time and successfully, but things started to change, at least with the 4 quarks, the tetraquarks, back at the start of the early 2000s, with most famously the discovery of what I still call the X3872 by Belle. So this beautiful and famous exotic hadron, which almost certainly is at least at some level a 4 quark state. And then others rapidly followed, the Z4430. And these discoveries have attracted a huge amount of interest. You might think that Bell's most cited paper would be that which made the measurement of sine 2 beta, but it's not. That's the second most. The most cited one is this observation of this particle, the X3872. And again, for LHCb, the most cited paper is not the one which is here in second place, the hint of lepton universality violation in B decay L plus L minus decays. Instead, it is the observation of petroquarks, which we'll now be speaking about. And these observations also excite not just the scientific community, but the greater public. So this is the reactions culled from the world's press to the LHCb study of the resonant nature of this tetraquark, the 4430, which showed it to be a real particle. And you see many headlines, including this rather worrying one in the middle, which I'm talking about opening the gates of hell, which I think came from Iran. So I'm not sure what they were smoking. And indeed, this study has inspired music. There is actually a rather beautiful piece, a saxophone quartet you can listen to, which was premiered at the Montreux Jazz Festival in 2014, entitled the Z4430. So people are interested in this stuff, and for good reason. Let's now talk about pentaquarks. So this is the one thing I want to focus on. This gives you some history of it. People looked for pentaquarks for a long time. Let me not dwell on this, but there were signals which appeared in the early 2000s involving rather light states where everybody was convinced that they saw a signal, but with more data, these signals evaporated. And you can read a review in the PDG of 2008 where Hicks describes this as a curious episode in the history of science. And I think it's more than curious, I think it's embarrassing. But what happened to LHCb? Well, people were studying lambda beta J psi proton kaon decays, and they were doing this for flavor physics reasons. They wanted to make CP violation studies. And one can get this very pure signal, a very large signal you see on the left. But if you plot, make the Dalitz plot, so you plot the J psi P combination against the KP combination, your eye is drawn to various things. So you see that there's vertical lines here, and this is what you expect. These are vertical lines which come from excited KP resonances, and you see this on the bottom left here. This is the projection. So these are all excited lambda resonances. But you expect nothing horizontally, but there seems to be a band here horizontally. Let me pick it out. And indeed, if you project that out, you see this peak here in data. Okay, so this is weird, because if this means that this is a J-psi proton combination. So if that really is a particle, that must have a UUDCC bar content, and this is manifestly exotic. It doesn't fit into the vanilla quark model. But one should not just jump to conclusions, because weird things can happen. These things can appear as artifacts of if you just the superposition of many other things happening. So what it's necessary to do a thorough analysis, or makes a full amplitude analysis of the J-psi proton kaon final state, and you put into this amplitude analysis everything that you could find in the PDG, which means all these lambda resonances. And you see here shown in red on the bottom left that this model describes these data very well. So these are the lambda resonances. These are not exotic. These are just excited lambdas. And then you see, if you look in the other projection, what this looks like. So this is shown here in red. And you see that this information, this fit involving everything in the PDG at that time, does not describe the data. So to describe the data, you have to put in these exotic particles. You have to put in one here, and also, though it's not clear from what we're looking at, you have to put in another one. So these we call PC states. These are pentaquark states, and the mass and the width for both of these were measured. So this was the first observation of pentaquark states. This was seen in J-psi proton K. They've also, evidence has been seen in the Bibo suppressed channel J-psi proton pion. That is a much lower yield, so you don't expect a throbbing signal there, but there is evidence that just what you expect is there. And more recently, people have looked in J-psi proton antiproton. You'd expect to see pentaquarks here also. Rather interestingly and curiously, the ones I showed you, they don't seem to appear here, but there's evidence that something does. This is shown in the J-psi proton, the J-psi antiproton projection. So this looks like it, if this is substantiated, this is also a pentaquark, but an excited pentaquark at slightly higher mass. So why this appears and the other two do not, we do not yet know. Following the LHCb discovery, our colleagues around the ring came to the party. So Atlas made a preliminary analysis. This is a very heroic analysis. But I want to use this slide to actually reinforce what I said previously, that hadron identification is absolutely critical. But for doing flavor physics, for doing spectroscopy, you need riches. On the right, you see the LHCb signal, J-psi proton K. So this is the lambda B signal, and it's beautifully clean. On the left, the signal from Atlas is there in green on top, but one has all this background underneath, and that's because Atlas, wonderful experiment though it is, does not have a rich. Nonetheless, Atlas can pick out this signal region and analyze it, and you see the analysis here. And this analysis is certainly compatible with LHCb's findings. That to describe it best, you need to include pentaquarks. However, with the quality of these data, that result is not conclusive. And an interesting footnote, and just to make clear why more data matters, what I showed you came out of the Run-1 data of LHCb. With Run-2 data, another analysis was performed. One has greater statistical precision, and one gets a structure which looks very similar to Run-1. But one sees that there's other things happening. So at the peak region, there seems to be a little more going on than first thought. And on the left-hand side, you see a definite peak emerging. There was a hint of this in the Run-1 data, and it's clearly there with the Run-2 data. So let me show that same thing zoomed in with the background subtracted. You see this left-hand peak, and you see that the central, the high peak we saw is now actually made of two peaks. This is very clearly the case. So rather than the original analysis had one peak and one broad peak, this analysis supports 3 narrow peaks. The broad peak which we had previously, that may be there, it may not be there. We can't be sure. This needs more data to be sure of. Let me now just to move on and conclude this discussion of pentaquarks, just to say that if pentaquarks now exist, you would expect to see them in other baryon decays. You'd expect to see other pentaquarks, not just the one which we have now been describing with the CC bar light quark content. You would hope to see one which maybe has a strange quark in it. So indeed, an analysis has been performed of psi b to j psi k lambda. This is a trickier analysis because the lambda flies. It's long-lived, so the efficiency there is lower than in the analysis we have been discussing. Still, one has something like 2,000 candidates with high purity, and there seems to be something going on in this projection. You see it there. So again, this is the j psi lambda projection. It's analogous to the j psi proton projection we were looking at previously. If there is a resonance here, it would be exotic. It would be a pentaquark. So a similar analysis has been performed, full amplitude analysis, not just a bump hunt, but here you see projections which show the bump. And on the left, there seems to be certainly something happening here at a mass just below 4.5 GeV. And on the right, we see the same thing, but in a region where the background from other resonances is lower. And one has a 3 sigma evidence of a resonance, which, if substantiated, would be a CC bar USD pentaquark. So for a better understanding of these puzzles, accompanied no doubt by more surprises, we need significantly larger data samples, and these are coming, and I will talk about those in my final lecture. But I've spoken for long enough, so let me conclude. So I believe very much that despite the formidable challenges, hadron machines, and hence the LHC, offer unbeatable opportunities for flavor physics studies. To exploit this potential fully requires a dedicated experiment with optimized geometry, instrumentation, and trigger, and LHCb is such an experiment. We had this digression on hadron spectroscopy. I'm not claiming that this is flavor physics, but it's a topic of incredible richness, ideally suited to flavor physics experiments. Hadron spectroscopy has been one of the most interesting and unexpected success stories of the LHC. But in our next lecture on Monday, we will turn back to flavor physics. I will focus on unitarity triangle measurements and CP violation. Thank you for your attention.
Okay, thank you very much, Guy, for this introduction to flavor physics at hadron machines. Are there any questions? I haven't seen any in the chat, but please go ahead if you have any. Maybe just to start, when you showed the B to HH plots to showcase the rich, you then showed how much is it improved with greater understanding. Is that just the improvements in the trigger largely that you can get more signal, or is that just improving the vertexing and things and reducing the background that way? So
I think both. The trigger improved in efficiency a lot as time went on, but calibration improved. The combination of all likelihoods involving all detector information were refined and improved. So one sees that if you compare these plots with these plots, you see both that the particle identification is clearly much better, and also the combinatoric background is much lower. So it's just hard work from lots of sources.
Okay. All right. So I don't see any other questions right now, but as you'll be back on Monday, if people think of anything, they'll have an opportunity to ask you then.
Yes.
So yeah, thank you very much, and